Welcome. Today is Tuesday, October 6th, 2020, and this is a NERI webinar intended to disseminate educational information and research outcomes around natural hazards and the built environment. Today's webinar is hosted by the Natural Hazards Research Infrastructures Computational Modeling and Simulation Center. The webinar is supported by the National Science Foundation under awards 1612843 and 1520817. Any statements in this webinar are those of the presenter and do not necessarily represent the views of the National Science Foundation. For more information about NERI and the SimCenter, visit the designsafe-ci.org website, where you can find links to the SimCenter and the NERI Learning Center, and also information about the facilities supported by NSF. Today, we're joined by Michele Barbado. Michele is professor in the Department of Civil and Environmental Engineering at the University of California, Davis. He is an expert in both traditional and innovative construction methodologies and materials, with particular emphasis on new, recycled, and green materials. He is active in the development of performance-based methodologies for earthquake, wind, and hurricane engineering, as well as multi-hazard applications. Dr. Barbado's research also embraces nonlinear finite element modeling, and analysis of structural systems, random vibration theory, structural reliability analysis, multi-hazard assessment, and mitigation under current and changing climate conditions. Essentially, he does it all. The title of his presentation is Hurricane Loss Analysis for Single-Family Houses Considering Current and Changing Climate Conditions. And Michele, I invite you to begin.
Thank you very much. Thank you, Matt. Thank you to the SimCenter for inviting me to present my work on performance-based hurricane engineering. I will immediately start with the outline of my presentation. I will have just a very short introduction and background for the work that I'm going to present. I will give a brief overview of the framework for performance-based hurricane engineering, and then I'll show a couple of application examples. One focusing on the comparison of the performance of different storm mitigation techniques for single-family houses. And then investigate the climate change effects on the performance of these houses with a few conclusions. So what are we talking about? We're talking about subtropical and tropical storms, hurricanes, typhoons, and cyclones. These are all storms that are formed over tropical oceans. And I'm confident that many of you are familiar with what we are talking about. They are happening every year on the Atlantic coast of the United States, on the Pacific coast in Asia, and more recently we had a few examples of typical tropical storms even forming in Europe, which is something quite new. Fundamentally, these are storms where the sustained wind speed is higher than 74 miles per hour or 119 kilometers per hour. How do these objects work? We really need to have warm ocean waters, in general with the temperature higher than 78 Fahrenheit, 26 Celsius. They need to be sufficiently north or south from the equator. They need to have a low vertical wind shear in the upper part of the atmosphere so that this cannot reduce the energy of the storm, and then some unstable conditions and a disturbance that will start overall the process. Fundamentally, the warm air with high humidity is pulled up, produces the energy to generate the rotation, and then it produces, when it gets cold, comes down in terms of rain. The hurricanes are generally classified using the Saffir-Simpson hurricane scale that categorize hurricanes into 5 categories based on the maximum sustained wind, from category 1 to category 5, where category 1 are, let's call it milder cases of hurricanes, while category 5 are catastrophic hurricanes. Let me point out that there is no limitation in the usage of the Saffir-Simpson hurricane scale, in which it does not account for other important characteristics of the hurricanes, such as, for example, the storm surge or the production of rain, that are all things that can increase significantly the devastation produced by hurricanes. So how do they act on structures? We are focusing on their effect on structures. Obviously, we have the effect of strong winds that produce pressure on the different surfaces of the different structures and can produce damage and collapse. But we have also windborne debris impact. And windborne debris impact is particularly important not only for the localized damage due to these objects that are projected at high speed from the wind, but also because once the envelope of a building is breached, the load path inside the building completely changes. You have internal pressure build up, and we see very often houses that look like they exploded, and indeed this is exactly what is happening. They pretty much explode from the pressure produced inside, for which they were not designed. Then we have storm surge and flooding. This is actually the major cause of death from hurricanes. Once the water is in a neighborhood, there is no way to escape, and it has been unfortunately known that when you have more than a few feet of water between the current and what is in the water, they are extremely dangerous for the life of the occupants of the structures. Finally, we have rain. Rain usually is something that can produce flash flooding, but anyway, produces a lot of the damage in the houses. Once the water is inside the house and the buildings, these buildings may require actually to be torn down and rebuilt because they become not sanitary anymore to be occupied. So the idea of this research is to build on top of existing performance-based engineering approaches, and we have a series of examples of approaches that have been developed during the years. Obviously, performance-based earthquake engineering, it's probably the first one. It has more than 25, almost 30 years of history at this point, but there have been also development for performance-based blast engineering, performance-based fire engineering, performance-based wind engineering, and most recently, for example, we have had ASC, SCI to develop a pre-standard for performance-based wind design, which will be also called in the next version of ASC 722 that is being currently developed. So performance-based engineering is a reality. It is a direction that our profession of structural engineers is undertaking and is most likely going to be here to stay. So what are the motivation and the objective of my research in performance-based hurricane engineering? We have discussed already how hurricanes can cause significant economic and societal losses, and we need an approach that can consider, evaluate, assess, and mitigate these losses in a rational way. And performance-based engineering has been demonstrated to be such an approach. In addition to that, we have deep uncertainty in terms of the effect of climate change. We know that one of the effects is to intensify hurricane actions. However, it is still existing research. There is a research interest in understanding these effects on the hazard and the expected losses in order to have some tools for the mitigation. And so performance-based hurricane engineering has been developed as a rational method for the prediction of wind and hurricane hazard under current and changing climate conditions, and to assess the effects on the expected losses for different types of structures. In order to explain the performance-based hurricane engineering framework, I'm going to start with the well-known peer performance-based earthquake engineering framework. This is really an application of the total probability theorem, where a divide and conquer approach is used, a difficult problem, the one of design of a structure considering the performance under different types of hazards, is broken down into smaller, more manageable problems. And in the case of earthquake engineering, it is broken down into 4 different steps. An hazard analysis steps that investigates and describes probabilistically what is the hazard at the location where the structure is going to be built or is located. The structural analysis phase, that is the one that us structural engineers are more familiar with, understanding the behavior of a structure once it is subjected to the different loads and effects coming from the hazard. Damage analysis is also something we are very familiar with. It's finding the probabilistic relation between the damage level in structure and its response under different loading. And then the loss analysis, which is a way of measuring the effects of this damage on the structure, quantify them in a way that then it can be used for decision making. So what is new in the performance-based hurricane engineering framework? The methodology is also based on the total probability theorem. It is useful to divide and conquer also this problem. However, hurricanes are a little bit different than earthquakes because they really need to be represented as multi-hazard scenarios. You have the wind, you have storm surge, you have rain, you have windborne debris. These are all correlated, happening at the same time, but depending on different parameters. And so based on what has been already developed in performance-based wind engineering, we moved from the performance-based wind engineering framework to the performance-based hurricane engineering framework by introducing these multi-hazard considerations. And particularly for the performance-based hurricane engineering framework, we are considering hazards that are synchronous because they're happening all at the same time. And that include also effect of cascading hazards in the sense that in a hazard that is producing effect on the structure can change, affect, or trigger other hazards that can be exacerbated or modified by the changes in the structure. So how does that look like mathematically? The triple integral of performance-based earthquake engineering becomes a quintuple integral in this formulation. The changes are really in the hazard analysis range. I'm actually identifying here with this red line the changes from the methodology. Structural analysis, damage analysis, and loss analysis are practically left as for the other PBE frameworks. However, the hazard analysis is different because now we have to consider the interaction of multiple hazards. Among the many effects of that is that your intensity measures are always vectorial because they need to represent the different hazards and their interaction. In addition, we have two new steps that are a structural characterization step and interaction analysis step. In the structural characterization, we are describing probabilistically the properties of the structure that can affect the load applied on the structure. This is a step that is not necessarily needed in earthquake engineering because the effects are usually included into hazard analysis. Think about structure-dependent intensity measures. So the two steps are practically put all together into an hazard analysis. And then the interaction analysis is the step where hazard analysis and structural characterization are put together in order to describe the actual effects of the hazard on the structure. And here I'm really thinking about objects such as pressure coefficients or natural periods, which depend on the characteristic of the structure and can change the load that is seen from the structure for any given hazard that is dependent only on the location. An additional contribution of this framework is the inclusion of chain effects that we were discussing before. So when we arrive to the damage analysis phase, a structure that is damaged changes also some of the parameters that characterize the structure, and thus the loads on the structure are changing. And this is really particularly significant when you have things like breaching of the envelope of a building, where obviously the properties of the structure are changing. This changes the pressure coefficients applied on the structure. And now for the same wind event, you have a much higher load that is applied on the structural component that make up our structure. And so building on this, it is possible to implement the framework in many different ways. The way that will be presented here, or the results that I'm going to present in this chat, in this talk, are based on a multi-layer Monte Carlo simulation approach. This specific implementation allows to break down each of the steps of the analysis into two sub-steps. A stochastic simulation step where we are sampling the random parameters that describe each of the different analysis components. And then an analysis step that is based on deterministic models, hazard models, finite element structural models, cost models that are used to produce the uncertainties and propagate them from one component to the next of our analysis. Notice that in this process for this simulation approach, we start by simulating the number of hurricanes per year because we are trying to generate a loss curve, an annual loss curve. In the case in which in our simulation there is 0 hurricanes produced in a given year, the analysis still runs with a non-hurricane wind at the location of interest. And thus, this methodology reduces to the wind, to performance-based wind engineering as soon as you have 0 hurricanes happening in a given year. So given this very brief overview of the methodology, I'm going to present the couple of examples that I had introduced before. The first one is comparing different storm mitigation techniques for residential buildings. We are considering a simplified the geometry for a real structure located in Pinellas County. This is a real residential development with the 201 wood gable roof structures. And we have assessed the value of the structure based on the square footage as about $200,000. The value of the content was assumed to be half of it, and so we are going to have this baseline as our costs. Geometrically, this is the unfolded view of the target building. We are considering the geometric parameters as deterministic, as we can measure those. And this is the location where the house is positioned geographically. We go now through the entire process of our simulation. We start with the hazard analysis. We have to model, obviously, the wind velocity for the pressure, and then the house is sufficiently far away from weather bodies so that we don't have to worry about flooding. And we need to really focus mainly on wind, pressure, windborne debris, and then the rain that can enter from these effects. We model the wind velocity at the location. We model the possible wind debris, windborne debris at the location, mainly produced by the cover of the buildings that are surrounding the structure. There is some vegetation in the location, but we are neglecting in this particular application the vegetation. So all of the windborne debris are produced by the other surrounding structures. And then we need to represent the characteristic of the structure that change the load. And these parameters depend on the geometry, on the orientation of the house with respect to the wind, on the location of the different portions. We found from the literature the probabilistic description of the pressure coefficients, external and internal, under enclosed breached condition, and under different direction of the wind. And then we evaluate the interaction parameters for windborne debris. We actually consider two different interaction parameters, the linear momentum and the kinetic energy of impact. And this is because other research, including ours, demonstrated that the linear momentum is the parameter that controls the behavior of elements that are brittle, whereas the energy of impact is the parameter that controls the behavior of tactile elements such as storm panels and other protective systems. We used an existing debris generation model and a flight description model for debris. We also need the pressure applied on the different surfaces. As you can probably recognize, this is the equation for wind pressure of on structural components and cladding that is used in AC 716, with the only difference that all of the parameters that are appearing there are now random parameters that during the simulation are sampled to provide the actual numerical value. And then we have the structure analysis and damage analysis component. For this type of structure, we are not really doing a finite element model. We are really comparing the load that is applied or our interaction parameters with the properties, the strength properties of the different components that are available in the literature. And finally, we can put all of these ingredients with a probabilistic cost model and obtain an annual probability of exceedance curve that expresses the probability of exceeding a certain cost of repair over a given year for the structure. And here, what we did was to consider the different hazards, first one independent from the other. You can see the red line corresponds to the loss due to windborne debris in hurricane conditions. The magenta line is the loss due to wind that is produced by non-hurricane events. And then the blue line is the one from wind due to hurricane events. The line for windborne debris from non-hurricane events is not represented here because it's practically, for any purpose, non-existent, is equal to 0. If you use these to evaluate some statistics of the loss, we are reporting here the annual, the expected annual loss, the standard deviation of the loss for a given year. You will see that if you sum up the expected annual losses from the different hazards, you actually obtain something that is around $1,000 per year. While if you include the interaction among the different hazards, that chain effect that is included in our methodology, you get something that is about 25% higher, $1,287 for this specific simulation. And so you see that in this case, you have some non-negligible interaction among the different hazards. And this really shows that in order to have a proper analysis of the hurricane effects, you need to include these interaction. We used this data for an extra step that is really to help in the decision of our analysis. And so we considered 4 different possible retrofit or design solutions. The addition of aluminum hurricane protection panels, the substitution of shingles with the clay tiles, and the changing of the roof sheeting nailing patterns. In this case, we considered 3 different nailing patterns for the roof sheeting. And then a drastic change of changing your structure from a wood structure to a masonry wall structure. If you combine all of these conditions, you have 24 different possible combinations of mitigation strategies. In order to compare them, we introduced a cost-benefit analysis of the retrofit, where the benefit is given by the summation of the difference in expected annual losses between the house as it is and the retrofitted house, with some discounting rate that is assumed here equal to 3% over a design life of 30 years. And then in order to get the benefit, we need to subtract the cost of retrofit at present time. This allows us to have a comparison of the cost of retrofit, the expected loss in 30 years of life. And then if we get positive numbers, that means we have an effective saving, a benefit. And if we have negative number, the negative numbers, that means that actually is not worth to do the mitigation strategy. So for this specific house, all of these 24 results are reported here. The first case is our baseline house with no mitigation. We see that changing the nailing patterns in the roof sheeting is actually very effective in terms of gaining savings. The usage of tiles is actually here not very beneficial. Actually, the cost of using tiles is really not justified in terms of the reduction of losses. Storm panels are also very effective and very cheap in reducing your losses, and thus produce a significant benefit. And then you can see that for this specific location and this specific residential development in this specific house, actually using a masonry structure is not justified in terms of costs and saving, which was actually a very nice discovery when I did it, because when I was building my own house in Louisiana, I was wondering if I should have done it in masonry, but I was refrained by the costs. And indeed, it was nice to have my research show that the choice was actually a rational one. So that's really a way of deciding what to do with this house. What changes when we include the effect of climate change? Because we are considering now structures that have to live, by our assumption, at least 30 years or more. And so let's do these further analysis. And we start by trying to model these climate change effects on the hurricane hazard. And we see that, first of all, the global sea surface temperature has increased significantly in the last 100 years. And the hurricane intensity have also increased in the same period. This makes a lot of sense because we have seen that is the high temperature in the water, the warm moisture that produces the energy that is needed to move the hurricane. Research has shown that the peak wind speed of hurricane increases between 5 and 10% for each Celsius of increase in the tropical ocean temperature. Another thing that is very scary in a certain way is that not only the hazard is increasing, but also the vulnerability of US and the world is increasing. And this is because the number of people that are moving and living along the coasts where obviously the vulnerability to hurricanes is higher is also steadily increasing. And so our risk is increasing because the hazard is increasing, but also the vulnerability is increasing. Now, let's try to obtain a model that can allow us to describe the effect of climate change within a performance-based hurricane engineering approach. We see that the identification of the hurricane actions is obviously highly correlated with the losses, and we need to predict the probabilistic hurricane intensification due to the probabilistic and measured increase in temperature that we have for climate change. We started with the IPCC, the Intergovernmental Panel on Climate Change, fifth assessment report, projection scenarios for both the sea surface temperature and the sea water level. We see that they are increasing, but depending on the different scenarios, there is a different variability, a different average change in temperature, a different average change in water level of the sea. So we investigated statistically what is happening in the Gulf Coast and the Atlantic coast of the United States. What we found is that the number of hurricanes per year doesn't change a lot. Doesn't change in terms of years, but more importantly, doesn't change in terms of the average temperature, annual temperature measured during the different years. What changes is really the intensity of the hurricane. And so we tried to develop a model to represent the description of these changes in intensity with the changes of temperature. The data that we have, unless we want to go into detailed models of meteorology and changes in climate, are the changes in annual average temperature. And we try to develop a statistics-based model based on linear regression of historical data that relates the temperature at the time and location of a hurricane with the annual temperature of a given year. Once we have these, we can generate similar linear regressions that produces a relationship between the mean and the standard deviation of the intensity measures that we have identified as most important to represent the intensity of a hurricane, that are specifically the peak wind speed over the profile of the hurricane, the distance from the center of the hurricane at the peak of wind speed of the hurricane, and the translational speed of the hurricane. And here the results of our statistical analysis, again, using information that represent the effects of hurricanes along the Atlantic coast and the Gulf Coast. In particular, we have considered 27-mile post at 100 nautical miles along the entire coast. And again, based on statistical data, we described for each of these locations a distribution of the distance from the center of the hurricane to the location of interest, a radius of influence beyond which the hurricane doesn't change really the risk and the wind speed distribution at the location, and obviously the frequency of hurricanes at the location that in this application has been modeled as a constant until better data is available to demonstrate otherwise. Based on this information, we introduced a wind speed profile model. This is actually a model that was published in 2005 by Willoughby. Is a less known model. That usually the model that is used is the Holland model, the Holland formula. However, the Willoughby model provides a larger number of parameters to work with and a better description of the profile of the hurricane, particularly far from the eye of the hurricane. I'm not going to enter into the mathematics of these, but the profile model describes the rotational component of the hurricane, and then it is combined vectorially with the translational component of the wind speed for the hurricane through the George model, that is the model presented at the bottom of this page. And now we have a model that produces a wind speed at a given location. Let's see how it works in terms of representing historical data, and also how it works for projection of wind speeds. And so the first comparison is done with the historical NIST data to see how we capture the body of the wind speed distribution. And as you can see, we have a model that produces very good results in terms of the mean wind speed, and it's still acceptable in terms of the standard deviation of the wind speed at the different locations. It's not as sensitive to the different geographical characteristics. However, if you look at the average error between historical data and the one produced by our model, we have errors in terms of mean and standard deviation that in average over the 27 locations are way smaller than 1%. So we were very satisfied with this model. Now we want also to see how this model works on the tail of the distribution, because if we are designing structures, we are more interested in the tail of the distribution than just in the body of the wind speed distribution. And this is a comparison of our model with the design wind speed provided by ASC 716 at the different locations for 300, 700, 1700, and 3000 years return periods. These are the wind speed that are used for design of category 1 through 4 structures in ASC 7. So they represent the tail of the distribution. And again, when we look at the relative difference calculated over the 27 locations, we have differences that are always smaller than 1%, and the maximum error or difference that we find in our estimate of these wind speeds with respect to the AC historical data is always smaller or equal to 10%. And finally, we compare our model that is all statistics based and so is extremely quick, is something that you can run for any location in a few seconds on a normal personal computer, with models that are actually using a much more computational intensive representation of the track of different hurricanes after reducing a scaling procedure for climate change representation. So completely different order of magnitude in computational cost. The black lines are our projection for year 2100, considering the two scenarios, RCP 8.5 and RCP 2.6. And the other dots and circles are the results from two models that are again using a complete modeling of the full track of the hurricanes from the Atlantic Ocean through the United States. You can see that again, these are the 300, 700, 1700, 3000 year points that we are representing here. You can see that the differences are really small from an engineering point of view. So our model is at least as accurate as very complex and computationally expensive models that are producing this data using a complete track of the hurricanes. So we are obviously very satisfied with our model. Now we want to see what this change in wind speed produces from a point of view of the effect on the houses. And so first of all, we have our, we measured our change of mean wind speed and standard deviation of wind speed. These are projections for the year 2060 with the scenarios RCP 8.5, which is the worst case scenario. We see that the increase in mean wind speed is somewhere between 6.9 and 9.5% over the 27 locations in these 45 years of time. The standard deviation is increasing more, and that is expected because obviously we have more uncertainties in predicting future wind speeds than current or historical wind speeds. But then we look at the changes in the design wind speed. Again, 300, 700, 1700, 3000 years. And here things start getting a little bit more scary because the design wind speed are increasing between 12.4 and 39.7%, which since the wind loads are proportional to the second power of wind speed, we are really talking about an increase in design wind loads that is contained between 26.3 and 95.2%. So we are almost doubling the design wind speed for some location and some structures. So what happens when we take the same house that we analyzed before? Now we are moving it here north of Miami. We were looking for a place with a little bit higher wind speed to see really the effects of these. And we go through the same process we did before by not considering climate change and by considering climate change with the worst case scenario. Again, we are considering the effect between 2015 and 2060. And you can see that in the first case, you have similar results to what we had before. Again, the nailing pattern works well, storm panels work well, masonry is too expensive. However, when you consider climate change, something that now would look like is too expensive, now it becomes actually feasible and reasonable in terms of expenses and cost benefits. And here you can extrapolate from these results on the effect globally of these losses. We are talking about when you multiply this by the number of houses and the locations and the years, we are talking about a lot of billions of extra losses that are going to be happening if we don't do something to retrofit our houses and our buildings. And with this, I think my time is close to the end. So some conclusions. We have developed a performance-based hurricane engineering framework that is based on the total probability theory and uses knowledge that was already developed in other civil engineering subfields like earthquake engineering, fire engineering. However, the performance-based hurricane engineering is the first framework for real multi-hazard performance-based engineering. This methodology can be used to evaluate, assess structural risk and loss associated with the structures that are in wind and hurricane-prone regions. We have used this methodology to compare the performance of different storm mitigation techniques applied to single-family houses. We have also developed a statistics-based model for wind speed prediction under changing climate conditions. And we have used this model to understand the effects of climate change on the performance of single family houses to understand and quantify the performance. However, the performance framework can be used for other types of structures. I've not presented other structures just for the time limitations, but we have some examples on tall buildings that have been already developed. And so it can be used also to calibrate design codes, particularly if we want to include the deep uncertainties that is associated with the effect of climate change for the future. And with this conclusion, I would like also to have some acknowledgements to the funding agencies that paid for this research, and also for acknowledge my collaborators, Dr. Petrini and Dr. Ciampoli. Ciampoli, unfortunately, passed away a few years ago. And then my students, Dr. Unikrishnan, who obviously already graduated, and Mr. Esmaili, that is still working with me and getting close to finishing and is really focusing on the climate change analysis and efforts. And with this, I'd like to thank you very much for your attention, and I'll be very glad to respond to any questions you may have. And also, if you want, my contact information is listed at the bottom of this slide. Thank you very much.
Thank you, Professor Barbato. It was a very informative presentation. And at this time, we'll transition to the question and answer session. Attendees are reminded that you can relay questions to the moderator using the chat window. And we do have a few questions, so thank you very much for staying with us. The first one is, how does the cost-benefit analysis presented in the case study compare to the projections in Mitigation Saves report by the National Institute of Building Sciences? And have you considered connecting the retrofit cases to fortified construction tiers?
So thank you very much for this question. This is actually a very interesting one. I think it is referring more to the other examples, but let's look at this one. So We didn't do a direct comparison between the effect in terms of global savings with our cost-benefit analysis because we really focused on the design and the decision process for a single building, whereas the analysis that you're referring to is something that looks at a group of a portfolio of buildings and houses over an extended region. And so we didn't do yet that homework. We did some back-end calculations to understand what these would entail in terms of global costs in terms of fortifying our structures. And we did it for Florida, where you have about 6.5 million of houses now, and you are expected to have about 7.5 million of houses by 2060. Our estimates shows that the effect of climate change by itself produces a $350 to $400 increase in expected losses annually for every single house. So when you take this loss, you multiply it by the number of years, assuming, for example, a linear increase with the inclusion of the increase in houses and over the period of time, you are really talking about an increase only for Florida of about 60 to 75 billions of losses due only to wind, windborne debris, only on houses. When you add the effect of flooding, actually you get an increase that is almost fourfold. This is what we get with our initial results that I'm not presenting here because we are actually still analyzing them. But we are talking about a very significant amount of money. And so, again, I thank the person that asked this question because we fully have intention to do this homework of comparing the two things. But right now, what I presented is really how we make a decision for a specific house, for a specific building, for a specific bridge, or for whatever structure we are trying to design, accounting for the climate change effects.
That's a good point. So if you're studying just an individual structure, is this approach practical at a regional scale? Is it appropriate, or is it, yeah, does it scale up to be able to study cities and regions?
So it does when you use it within a catastrophe modeling approach, in the sense that the way that I envision the performance-based hurricane engineering framework to be used is not to analyze all of the 7 million of houses that are in Florida, but in analyzing all of the structures that are critical structures. So hospitals, bridges, structures that are particularly important for the response, the first response after a hurricane, for which you cannot really use the smoothed statistical approach that is typical of catastrophe model. And so you can use a catastrophe modeling that is really for these single houses type of things, gone with the performance-based hurricane engineering that is applied to critical structures or structure of particular importance. The other way you're using the performance-based hurricane engineering framework is not only to make a decision on the single house, but also how do you want to improve your design codes? What makes sense to do? That is something that you can use because you are analyzing single structures in that case and seeing what are different approaches produce in terms of performance. But you would not model 7 million of houses. You can get the fragility curves for a family of houses and then improve catastrophe model by producing more accurate fragility curves. But you do not model 7 million of houses with this approach. It is quick, but it's not that quick.
Okay. One person's asking about the differences between this performance-based hurricane engineering methodology and other methodologies like the HAZIS framework or the Florida Public Hurricane Loss Model. Can you just pick up on some of the key features that distinguish these approaches?
Yes, so it is again going back to, are you doing a catastrophe modeling at a regional scale, or are you designing a specific structure? In ASUS, in the Florida hurricane public loss model, you are really taking the variability of structures that is driven by the fact that structures are multiple, are different, being built in different times and all of that. Here you are really representing the location of that specific structure within that specific residential development. So all of the windborne debris that you are generating represent that specific situation, not a generic typical situation that is more representative of a region. It may seem like shooting a fly with a cannon when you apply it to a single family house, but it makes even more sense when you are talking about a building that has a value of a few $100 million, or a bridge that if it's not functional after an hurricane will stop an entire region from doing what is needed in terms of first response. However, you can see that even for this application where everything is done in a statistics-based approach, and so probably it's not as accurate as those models that we have shown where you're actually tracking the hurricane, you can get very important information that are specific to that building, to that house. We are still talking about an analysis that takes a few seconds for each of these cases for a house, because for this type of structure, you don't need to really do a finite element analysis model to describe the behavior. While if you are doing a 70-story building or a large span bridge, you would really need to do a finite element model to understand what is the response of that structure under wind actions. So the difference is, again, you are here focusing on a single structure as you would do for earthquake engineering. You are designing that structure. You are not trying to evaluate what is the loss for a region, which is what ASUS and the Florida Hurricane Loss Model, public loss model, are trying to do.
Mm-hmm. We're about out of time, but there's one last question. If you could comment on how to validate your analytical framework with either real loss data or experimental or field verification. Are there any ways that these sorts of validations, have they been done, or is there a way to incorporate them into the framework?
It is quite difficult to validate these for a single building, because the data that you generally get is a cumulative set of data from an actual disaster that happened, and there is a lot of variability within the single structure. In fact, if you have seen the standard deviation that you use by applying this methodology, they happen to be of the order of 5 to 10 times the mean value of the house. And that is because in hurricanes and even more in tornadoes, what you get is something that is a hit or miss. If the hurricane happens to pass on top of the house, most likely it's going to be destroyed. And if it actually misses the house, then the house may be completely fine. So it's kind of difficult to do it for a single structure. And I don't know if it actually makes sense to do that for a single structure, but these results are consistent with the aggregate data that you obtain when you do when you get data from losses of insurances, or when you get data on damage from direct observation after events. And that is for the current conditions. For climate change, everything has another layer of uncertainty because even the projections that we are using have the uncertainty of projecting in the future, and also we don't know which scenarios is actually going to happen. The scenario that I'm using is the RCP 8.5. And now it seems like we may be a little bit better than that, but not much. So we are really in a deep uncertainty. And it's really difficult to come up with an experiment that says, okay, I can validate it. It's really more, let's wait and see what happens. And then you can both check your results once they happen. In a certain way, as we did in validating our wind model, where we developed our model and then we checked the body of the distribution and the tail of the distribution based on historical data.
Great, thank you for answering those questions. We're at the conclusion of today's SimCenter webinar. On behalf of the attendees, thank you, Professor Barbato, for this great introduction to hurricane loss analysis in a performance-based engineering framework. To the attendees, thank you for your questions. For additional upcoming NARI webinars, please check the SimCenter's website at simcenter.designsafe-ci.org and check your inbox for emails from announce@designsafe. These will have registration links to other upcoming webinars. Thank you for attending today's webinar, and thank you, Professor Barbato, for this.
Thank you very much. Everybody have a good day. Stay safe.